In my last class, I have completed a complete description of this elevation of boiling point, the second qualitative property of this dilute solution. Now it is my turn to derive this Raoult's law thermodynamically using the concept of the chemical potential. You know here this liquid is the solution of a non-volatile solute in a volatile solvent, and here it is the pure solvent vapor, and this contains in a cylinder fitted with a piston, and this piston is under the external pressure P. So this is also this external pressure equal to the vapor pressure of this liquid in which these two are in equilibrium. So actually this temperature is a boiling temperature of this solution under the external pressure P, at which this vapor of this solvent becomes equal to the external pressure. And you know this T is a function of this pressure and x1. If we raise this external pressure, this is P, the external pressure. If we raise this external pressure, then boiling point of the solutions will also increase. And this relation of this external pressure with this temperature has been elaborately discussed in Clausius-Clapeyron equation. And also in this solution, x1 is the mole fraction of the solvent. So whenever the x1 is lower, or you can say x2, mole fraction of the solute is greater, the boiling point, this T will also increase. Means here the boiling point depends on this external pressure and also the mole fraction of the solvent or mole fraction of the solute of this solution. Now these two solvent remains in two phases, in vapor phase and in the solution phase. In the vapor phase it is remaining in pure state, and in solution it is in mixture. So there is an equilibrium. So the solvent, actually we can write the pure solvent in vapor phase is in equilibrium with this solvent in solution. So the thermodynamical condition for this equilibrium, whenever a substance remains in two phases at equilibrium, the chemical potential of that substance in between the two phases becomes equal under a constant temperature and pressure. So actually it will be mu1 naught V equal to mu1 L. A naught superscript has been given for this solvent in vapor phase as it is in pure state. But here the solvent in liquid phase remains in a mixture, so superscript 0 is omitted and it is at a constant T and P. P is the external pressure, T is the boiling point of this solution under this external pressure P, and this x1 also fixed. If we expand this one, then mu1 naught L plus RT ln x1. This chemical potential of the solvent in solution is expanded in this fashion. This is the chemical potential of the solvent in liquid phase, in pure state and x1. This relation we can write only when this solution behaves ideally, or we can say it is valid for this ideal diluted solution. And now this has been transferred in the left hand side, and dividing by T we have mu1 naught V divided by T minus mu1 naught N divided by T is equal to R ln x1. So actually this now I can differentiate this whole equation with respect to temperature at a constant pressure. We like to see how the temperature varies with this mole fraction of the solvent or mole fraction of the solute which has been given by this Raoult's law. So differentiating with respect to T at a constant P, we have del by del T and mu1 naught V by T at constant pressure minus del by del T and here mu1 naught L divided by T at constant pressure. This one equal to R third bracket del by del T into ln x1 at a constant P. Now we can use the Gibbs-Helmholtz equation to convert this term into the molar enthalpy of this solvent. We have the Gibbs-Helmholtz equation. Gibbs-Helmholtz equation is del by del T and here G by T at a constant pressure equal to minus H by T square, where G and H are the free energy and enthalpy of a state of the system, and pressure is constant. In case of our system, this we are considering the molar free energy of this pure state, and this again will be the molar enthalpy of this solvent in pure state. So in our case, this will be del by del T, and here mu1 by T at constant pressure equal to minus H1 bar divided by T square. H1 bar is the molar enthalpy of this solvent. In short, molar enthalpy of this solvent, here it is the chemical potential of this solvent. When we apply this relation to this equation, we have here minus H1 naught bar V by T square minus H1 naught bar L by T square, and this one equal to R d ln x1 by dt. So these are applied for the pure state for 1 mole of this solvent. This is for the vapor phase and this is for this liquid phase. Now we can write here this minus third bracket, and here it is H1 naught bar V minus H1 naught bar L, and divided by T square, and T square is common, and this one equal to R d ln x1 by dt. So this value numerator gives the molar latent heat of vaporization. We are considering the vaporization. We are considering the vaporization of 1 mole solvent under the temperature T and pressure P. So this would be liquid undergoes to this vapor. So its value is H1 for this state. This value is the molar enthalpy of this pure solvent, and in this liquid phase, and here it is this one in this vapor phase, molar enthalpy of this pure solvent in vapor phase. So this by this final minus initial, this will give you the H1 naught V minus H1 naught L, and this will be equal to delta H1 naught bar. This is the molar enthalpy change for the molar enthalpy change for the solvent from liquid to vapor. And this one we can write. LV not a bar, and it is the molar latent heat of vaporization of pure solvent. So not is given means it is meant for the pure solvent. Now instead of writing this one, we can use this minus LV naught bar, R coming here, and here dt is going there, and there is a T square, and this one equal to the d ln x1. d ln x1. dt coming here, T square, and this one is LV naught bar divided by R here. So if we do this integration, how the x temperature is changing with this x1 of this solvent in solution, and when x1 equal to 1 means it is the pure solvent. In this case, this boiling point is del TB naught. It is the boiling point of this pure solvent, and here it is x1 means it is this boiling point of this solution. If we do this integration, then minus LV naught bar divided by R, and here minus 1 by T, and the limit is the TB naught and upper limit TB, and this is equal to ln x1 minus ln1. Or you can write minus LV naught bar divided by R, and here 1 by, if we eliminate this minus sign, then TB naught will come first, then it will be TB naught minus 1 by TB, and this is equal to ln x1 and ln1 equal to 0. So here we can write again LV naught bar divided by R and TB naught minus TB. TB minus TB naught and divided by TB and TB naught equal to ln x1. You can remember in my last class I have stated this TB minus TB naught is the elevation of the boiling point of this solution, and since TB and TB naught are very close together, as I have seen in a problem in this last class, so this could be written as LV naught bar divided by R and del TB divided by TB naught square, and this one could be written as ln 1 minus x2, or I can write here del TB by del TB equal to if since x2 is much less than 1, solution is very dilute, so this 1 minus x2 could be written as a minus x2. So the relation comes like that. The relation delta TB equal to R TB naught square divided by LB naught bar, and negative sign cancels from both sides into x2. It is very clear that delta TB depends on the mole fraction of this solute in solution, and this one is constant. This one is constant for the solvent. TB naught is the boiling point of this pure solvent. It is the molar latent heat of evaporation of this pure solvent. So this property within this third bracket is the constant, and that depends only on the nature of the solvent. Different solvent will have this different value. Now, if we like to change apart this mole fraction of the solute in terms of molarity as done by Raoult himself, then x2 equal to n2 divided by n1 plus n2. This is the mole fraction of the solute in solution, and this one could be written as n2 by n1, as n2 is much smaller than n1. Solution is very dilute. So this could be written as W2 by M2. M2 is the molar mass of this solute. This is the weight taken of this solute in solution, and here W1 and divided by M1. This is the molar mass of this solvent, and this is the weight or income of the solvent taken in this solution. So this one will be equal to W2 into M1 divided by W1 into N2. So instead of writing this x2, we can write here this delta TB equal to R TB naught square and divided by LB naught bar and into W2 into M1 divided by M1 into M2, or del TB, elevation of boiling point this solution is equal to RTB naught square, and this M could be taken here. This LV naught bar divided by M1, and it is to be multiplied by 1000, and here 1000 to be here 1000 multiplied, and here 1000 to be divided, and so it will be 10 to the power 3 into the W2 into 10 to the power 3 divided by W1 into L2. Or we can write here delta TB equal to RTB naught square, and here it is 10 to the power 3, and it is whenever the molar latent heat of evaporation is divided by this molar mass of this solvent, it will give you latent heat of evaporation of this per gram of this pure solvent, and that would be written as LV naught. LV naught, and this can be taken in a bracket, and this one is W2 into 10 to the power 3 divided by W1 into N. So this one again, I can mention this one is a constant for the solvent, and this is the molality according to our definition. So this relation I can write here, this delta TV equal to KB into AM, where KB equal to RTB naught square and divided by 10 to the power 3 small LB naught. If we like to calculate this value of molar elevation constant for water, then for water, this AB equal to R, you can write R calorie mole inverse Kelvin inverse into, if we consider the pressure is equal to 1 atmosphere, then the boiling point of this pure solvent is 100 degrees centigrade, or you can write 373 Kelvin square, and divided by 10 to the power 3, its unit is gram kg inverse, and this one is 540 calorie per gram. This latent heat of evaporation for this pure solvent per gram for water it is 540 calorie per gram. If we put calorie and calorie is cancelled, gram and gram inverse cancelled, so this, if we do calculate 0.513, and this 1 Kelvin still there, and it go upside, so kg, and it is the mole inverse, or you can write 0.513 Kelvin molar inverse. So this is the derivations of this Raoult's law using this chemical potential, and which I think very superior than other forms of this derivation of this law. And not only that, from this derivation we get this expression of this Kb, and from which this Kb of any solvent could be calculated by using this formula. So now, one homework in this context I can give here. For a certain solvent, BP is 127 degrees centigrade, and the latent heat of evaporation is 120 calorie per gram. Find the molar elevation constant. It has been set in Baroda University 2003, and the answer will be equal to 2.66 Kelvin kg mole units. So I request you to do this problem by yourself at home and find the result. During this derivation, I can here show two aspects. One aspect is that when the solute is volatile, means a solute is volatile, dissolved in a volatile solvent also. So in this case, in this picture, I can show here it is a cylinder fitted with a piston. Piston is under the pressure P, external pressure, and here the solvent in solution. Here the solvent in a mixture with this solute in vapor phase. So these two solvent remains in equilibrium between the two phases. This is vapor phase and this is the solution phase. So the thermodynamic condition for this equilibrium is that mu1 V equal to mu1 L. The zero superscript is omitted as none of these are in pure state. Now expanding this to, we can write mu1 not V plus RT ln x1 dash. X1 dash is the mole fraction of the solvent in vapor phase, and this one equal to mu1 naught and L plus RT ln x1. X1 is the mole fraction of the solvent in solution phase, and these are their standard values. So if we bring this one in the left hand side and divide by T, then mu1 V by T minus mu1 naught A divided by T, and this will be equal to this R and ln x1 minus ln x1 dash. Now differentiating this with respect to temperature at constant pressure. Pressure is constant. External pressure remains constant always during this derivation. And this, whenever we are differentiating this one, del by del T, and here mu1 naught V divided by T, and at constant pressure minus, here also del by del T, and mu1 naught L divided by T at constant P equal to this R and del by del T, and here ln x1 plus minus ln x1 dash. Third bracket close. Now we have seen that the left hand side will be equal to minus LV naught bar divided by R. R is coming here, and dt is going there, dt, and divided by T square, and this one equal to d ln x1 and minus d ln x1 dash. And these details of this step are not given as I have done just now in this derivation of this equation. So if we integrate, then here x1 dash equal to 1, x1 equal to 1 means it is the pure solvent vaporizes, and in this case then it will be the boiling point of this pure solvent, and when it is x1 and it is x1 dash, and this will be this boiling point of this solvent. So if we do this one, then minus LV naught bar divided by R. This is the molar latent heat of evaporation for pure solvent, and here this integration is minus 1 by T, and TV naught and TV here, and in this case equal to ln x1 minus ln x1 dash, integration of this one. So if we put this limit, then it will be LV naught bar divided by R, and delta TV divided by TV naught square, and this one equal to ln 1 minus x2 minus ln 1 minus x2. x2 is the mole fraction of this solute. Here x2 dash. Here it is mole fraction of the solute in this paper, and here is the mole fraction of the solute in this solution. So if we consider the x2 and x2 dash are very small in comparison to 1, then it could be written as minus x2 and plus x2 dash, or equal to x2 and 1 minus x2 dash divided by x2. And this ratio, this x2 dash divided by x2, let it be k. Say it is represented by k. So this one will be equal to x2 into 1 minus k. So delta elevation of boiling point of this solution when this solute is volatile, this will be equal to R minus cancels from both sides, and TV naught square and divided by LV naught bar and x2 and 1 minus k. We have seen here this value is equal to, or delta TV equal to KB into M and 1 minus k, where k is having this value. So 3 cases. In this case, we may consider the 3 cases one after another. Suppose x2 dash equal to 0, or say k equal to 0. K equal to 0 means x2 dash by x2 dash equal to 0, and solute is non-volatile. Solute is non-volatile since the mole fraction of the solute in this vapor phase equal to 0. So in this case, if we put here, then delta TV equal to KB into M, and this is Raoult's law. This is the Raoult's law. Raoult's law is obeyed. And second case, this one, and second is k less than 1. Then x2 dash by x2 less than 1, or x2 dash less than x2 means solute is less volatile than solvent. In this case, In this case, we can write the delta Tv is less than Kv into N. As the relation is delta Tv equal to Kvn into 1 minus K. So in this case, there will be elevation of boiling point, but this elevation of boiling point will be less than it would be expected from this Raoult's law. At the third case, when K is greater than 1, in this case x2 dash is greater than x2 means solute is more volatile. Than the solvent. In this case, this delta Tv, here K is greater than 1, so this one is negative, delta Tv is negative. Delta Tv means Tv minus Tv naught, and this one equal to negative. It means that the Tv naught is greater than a Tv. It shows that there will be depression of freezing point, means the solution is having the boiling point less than the boiling point of the solutions. Means here there occurs the depression of boiling point whenever the solute is more volatile than the solvent. Then second aspect now. This delta Tv equal to R Tv naught whole square divided by LV naught bar into x2. This one. It means that delta Tv depends on the nature of the solvent and the concentration of this solution. But if we divide this term with this delta, if this term, elevation of boiling point, is divided by Tv naught, then what happens? I like to see. Then here it will be R Tv naught divided by LV naught bar into x2, or we can write R by LV naught bar divided by Tv naught, and or I can say R divided by LV naught bar divided by Tv naught into x2. This Tv naught is coming here. But Raoult's rule that I have described while we have shooted this video lectures on this chemical thermodynamics. Raoult's rule shows that LV naught bar divided by Tv naught equal to constant, and this one equal to 21 calorie constant for non-polar simple liquids, and this constant is equal to 21 calorie mole inverse Kelvin inverse. So instead of this one, we can write this delta Tv by Tv naught, and this one equal to R by 21, and this is x2. It shows that this ratio now does not depend on the nature of this solvent, but depends only the concentration of this solution. So this is also another feature while we are deriving this relation delta Tb equal to Kb into Ab. This is all about the elevation of boiling point. In my last lecture, I have described the elevation of boiling point, and in case of second lecture today, I have derived the Raoult's law of elevation of boiling point from the concept of the chemical potential. So thank you all who are watching this video. In my next class, I shall try to explain the depression of freezing point of a dilute solution. Thank you.